Okay, so I think we're recording now. So in the next probably 3 or 4 meetings, we'll be looking at numerical linear algebra tools na pwedeng gamitin in data science. So basically, andito tayo kahit Friday na. Yan. Nakalimutan ko rin may klase na pala ngayon. So hindi pa pala tayo pwedeng mag-weekend, pero we need to look at numerical linear algebra as part of this course, mathematical data science. So basically, here's based on your expectations, kahit minimal lang, and the things that I browsed through in preparation for this class. Maybe we can have the following short outline for this section. Probably we can take a look at matrix factorization methods. So I'm thinking factorizations. So I'm thinking we can take a look at LU factorization. So nandito na yung Doolittle's factorization and Kraut factorization. And then another type is QR decomposition, or how do we decompose a matrix into a product of an orthogonal matrix and a right triangular matrix. And then probably if we have time, we can look at Cholesky factorization. Medyo special mention si Cholesky factorization because this is usually used in principal component analysis, especially for large matrices, and mas efficient siyang gamitin. And probably I want to introduce some more topics like how to solve rectangular systems, because we are usually akin to solving systems that are characterized by square coefficient matrices, right? So we are solving systems of the form AX equals B, where A is an M by N matrix, or an N by N matrix consisting of, say, real entries. So by the way, I'll be using several notations throughout the class. So if I forget to define them, pakisabihan na lang ako. Especially I am using materials from different classes that I already taught in the past semesters. So like this one, curly M is the set of all matrices. And then yung subscript, siya yung nagsasabi kung anong size ng matrix. So in this particular case, there's a single number in the subscript. So that means ito ay isang square matrix with n rows and n columns, right? And this is a classical linear system that we were taught how to solve, say, in our college algebra days, right? So na kapag ka meron kang isang matrix na kaya mong isulat, kung meron kang isang linear system that you can write in matrix form, AX equals B, where A is n by n, and your vector of unknowns is an n by 1 vector, then your right-hand side is an n by 1 vector again. And if A is invertible, or equivalently, if its determinant is not equal to 0, then there exists a solution, right? A unique solution, X equals A inverse of B. But again, provided that A is invertible, so meaning the determinant of A is not equal to 0, right? So ito sana, perfect na sana yung pagsasolve ng linear system, except for two big issues. Number one, not all matrices are invertible. So there's a big question on whether A is invertible or not, okay? And yung second issue or actually meron pang sub-issue yon, kung nagkataon na invertible nga siya, paano naman natin siya isosolve? Well, if you have a 2x2 matrix, andaling computin nung inverse ni A, right? It's just 1 over the determinant times a 2x2 matrix form by interchanging the main diagonal entries and negating the off-diagonal entries. Tapos ka na, right? Pero pag nag 3x3 matrix ka na, yung system mo ay 3x3 na, medyo mahirap na siyang kuhanan ng inverse. And usually you will ask the aid of computers to do the inversion for you. And then once you have inverted your matrix, you multiply it to the right-hand side vector B, and then you'll get your solution X. Pero again, hindi ganun kasimple ang buhay, because when you are doing actual research using real-world data, malaking matrix A. And computing for A inverse is not an easy task even for computers. Number one, for a large type of matrices or a large proportion of matrices, mahirap computin yung A inverse. And if you can't compute A inverse, yung machine precision o yung yung error due to machine calculations like round off errors and propagated errors ay makakaapekto dun sa A inverse. So basically, computing A inverse, if it exists, is not just a very expensive process, but is also an ill-posed process for most matrices, right? So yun yung unang issue, yung mystery behind the inverse of a matrix, whether it exists, and if it exists, how can we compute it efficiently and accurately? So that's the first question. Well, the second issue for linear system is that not all matrices or not all linear systems are square in form. So posibleng magkaroon tayo ng AX equals B kung saan yung ating matrix ay rectangular. So meron kang AX equals B, wherein A is, say, M by N, all right? So it's an M by N matrix. Delayed yung aking share screen, so hopefully nakikita nyo pa siya, with real entries, right? So nandun siya nanggagaling. And then our vector of unknowns is basically an N by 1 matrix, or it's an N by 1 vector. And the right-hand side is actually an M by 1 matrix or an M vector, all right? So paano tayo magsosolve kapag ganito yung nangyayari? And usually, I think in data science, you will encounter lots of linear systems wherein hindi square yung rectangular matrix. Kasi for instance, if X represents the parameters that you want to extract from a set of data, halimbawa meron ka lang, say, kunwari, meron ka lang 100 parameters na hinahanap para dun sa model mo. And then you have, you want as many data as possible, right? So you want to measure some, say, you want to measure some data to get some data, like, for instance, height of persons or their blood pressure and so on. So malaki yung gusto mong right-hand side. And this would be the available data for us. Say you have 1,000 of them, 1,000 data readings, right? So ibig sabihin, kung makakabuo ka man ng data ng isang linear system that will relate the 100 unknown parameters with your 1,000 data, and you want to use this 100 parameters to classify or to aggregate some data, yung matrix A mo ay hindi square matrix. So it's going to be what? What will be its size? It will be 1,000 by 100. And of course, 1,000 by 100 matrix is not invertible, because matrix inversion is only defined for a select class of square matrices. Yun nga mga square matrices na ang determinant ay non-zero. Okay? Now, I don't know if you have encountered the solutions to rectangular systems before. Can I see a show of hands? Sino na yung nakapag-solve na, or sino naka-encounter na ng pag-solve ng rectangular systems? Kasi isa to sa mga topics na wala dun sa outline. But I think it's very important, so I want to introduce this to you as part of numerical linear algebra. So si Ivy hindi pa. Lalo na tayo, no, tinuturo lang natin lagi ay square matrices, ano? Okay, so I think this is a good addition to the course, and because ganito rin yung ginagamit ko in my research, because isa tong ang ginagawa namin ay isang inverse problem. And usually in inverse problems, we want an overdetermined system. Okay? Para mas malaking chance na makakuha kami ng magandang solution. We don't want a system na rectangular, kasi gusto ko nga yung right-hand side vector ay maraming points, because we are discretizing a domain or a compact object. So hinahati namin siya into a mesh of points. And of course, yung mga nakapag-finite element methods na dyan, or essentially kahit anong modeling or anong klase ng mathematical problem, gusto mo laging dinidiscretize yung sample into a large number of data points just to capture the essence of the right-hand side. Okay? So gusto mo, malaki yung dimension ni B. Gusto mo maraming rows si B para marami kang data, because each row in B represents a certain data. Okay? Pero gusto mo yung degrees of freedom ay kakaunti, because the degrees of freedom will tell us ano yung mga dapat kong ma-achieve, or ano yung mga kailangan ko. Halimbawa, I'm doing a control problem. Etong mga parameters na nasa laman ni X, siya yung magsasabi ano yung kailangan kong mga parameters para ma-match yung data na B. And you don't want your parameters to be as much or as many as your data points. Kasi parang mahirap na siyang i-instantiate. So you want X to be as small as possible, all right? Minimal number of parameters, but you can match as many data as possible, right? So yun. So titingnan natin paano nagsosolve kapag rectangular yung system. And then we'll be looking at the concept of the Moore-Penrose pseudo-inverse. And actually, this will also work whenever your matrix is not invertible. Pwede natin siyang hanapan ng pseudo-inverse kasi lahat ng matrices ay may pseudo-inverse. Mapa-determinant niya ay 0, mapa-rectangular siya, it always has a pseudo-inverse. And the nice thing about pseudo-inverses, ang pseudo-inverse ng isang invertible matrix ay yung sarili niya. Alright? That's why most programming languages, pag pinasolve mo sa kanyang isang linear system, kahit invertible yung matrix A, ang kino-compute niya ay yung pseudo-inverse. Alright? Halimbawa kay MATLAB, meron kang AX equals B na pinapasolve. By default, ang gagawin ni MATLAB ay X equals, ito kasi yung syntax kay MATLAB pag solve ng isang linear system. Na-define mo na si matrix A, meron kang right-hand side vector B, sabihin mo sa kanya, okay, solve mo yung linear system na yan, and the command is A\B. Alright? So, ang idea rito ay, kung si A ay invertible, the ideal solution is A inverse B. Pero dahil nga computationally expensive, yung pagko-compute ng A inverse, hindi yun yung gagamitin niya. Ang gagamitin niya ay pseudo-inversion. Kasi ang pseudo-inversion naman, kung invertible yung matrix mo, ang ibibigay niya sa akin ay ang pseudo-inverse ay equal dun sa actual inverse. So by default, ang ginagawa ni MATLAB, instead na itong command na to gawin niyang inverse of A times B, ang ginagawa niya ay pseudo-inverse of A times B. So we will take a look at this kasi wala pa palang naka-encounter sa inyo nito, and how to improve the solution with respect to stability. Because all of the measurements we take are tainted with noise. Kahit sa inverse problem, mapa data science, and especially if you're taking physical measurements. Now, you might be happy with the theory that you can develop. Meron kang AX equals B, masaya ka na kasi natutunan mo na paano mag-solve ng linear systems, mapa-rectangular, mapa-invertible, and so on. Meron kang AX equals B. Kaya lang ang problema, kailangan nating mag-take into account ng isang bagay na ang ating data ay hindi perfect. Right? Especially if you're doing a physical experiment and then your right-hand side consists of data readings or measurements from say from a noisy data pool, or actually kahit physical measurements yan, hindi mo talaga sinusolve yung ideal system na AX equals B. Kasi nga tainted by data noise or by measurement error yung right-hand side na B. Kaya essentially, ang na-formulate mo, ang nai-input mo sa computers mo ay AX equals B plus some noise epsilon. Where the size of epsilon, say ang norm ni epsilon ay maliit kay 1. So usual measurement errors ay 1%, 0.5%, or 5%. Alright? So this, dito E, dapat to ay epsilon. And you will be surprised that even if you solve the perfect system, right? So if you solve A inverse, or you compute for A inverse, you apply it to both sides of your equation, so you'll get X equals A inverse times B plus epsilon. This is your naive solution, all right? Or yung naive reconstruction mo nung solution, pero you'll be surprised that even if, say, epsilon is 1%, and you computed A inverse exactly, right? There would be a big problem. Because there's a big chance that what you get as a solution X here, let's call it, say, X tilde, para i-represent yung solution X from the noisy or from the data that is tainted by measurement error, ay masyadong malayo dun sa solution na X star nung actual problem na sinusolve mo. Alright? So, and that will be a big problem because you computed your parameters X tilde based on noisy data. And you might be complacent na, okay, ito na yung gagamitin kong parameters. Pero yun pala, you failed to take into account that the data or the right-hand side data that you used for X tilde is tainted by a small measurement noise or a small error, okay? Pero yung difference between X star and X tilde might be very significant. So ibig sabihin, hindi mo na model ng maayos yung phenomenon. You have you obtained a very different set of parameters that you want to model your data. But what you have modeled perfectly is B plus epsilon, an erroneous set of data points. And the problem is, paano kapag ka malayo yung X tilde sa X star? So for those particular instances, we'll take a look at regularization techniques. These are techniques that are designed so that the relative change in the solutions we obtained from perfect data and from data tainted by noise will be proportional to the size of the noise itself, right? Gusto ko halimbawa 1% yung measurement error, so dapat yung relative difference ni X tilde at saka ni X star dapat around 1% or 5% lamang. Hindi siya dapat lalayo, all right? So naive reconstructions will not always give us, and most often it will give us very far results. Kaya gusto natin mas malapit sana sa katotohanan yung set of parameters na masasolve ko dun sa actual set of parameters that models the perfect data kahit na tainted by noise or error yung ating gagamiting right-hand side. So basically that would be, lagay natin siya dito, regularization techniques. And then after this, maybe we can take a look at particular applications. Oh, by the way, anong programming language ang ginagamit niyo sa dito sa class na to? Meron bang prescribed?
Sir, ano po, wala pong prescribed si sir.
Okay,
Depende
so
daw po sa amin.
all right, so free tayong gumamit ng kahit ano, no? So probably I'll use MATLAB. So kung wala pa kayong kasi nawi-weirdohan ako sa syntax ni Python, ano. So kung wala pa kayo, probably over the weekend, try to find or install MATLAB into your computers. If you want to follow my programming or para magamit niyo yung mga codes na sinulat ko. But if you don't want to learn another programming language, it's perfectly fine. You can stick to your own programming language or yung programming language that is more comfortable for you. Paki-translate na lang yung syntax na ginagamit ko kay MATLAB into your programming language. Okay? So siguro tingnan natin yon when we go to applications, right? So I think that's the plan. Do you have any other suggested topics? Actually, marami na to kasi yung 15 or 20 minutes for today ay naubos ko na sa paghahanap ng internet signal, ano. All right, so any other suggestions? Wala na? Masyado na ba yung marami? Okay, so let's try to cover the most out of these bullets. And I guarantee you, hindi nyo lang to magagamit sa data science, pero in any research that you'll be doing that involves linear equations, right? And usually in nature, halos lahat naman ng mga phenomenon is either linear in nature or reducible into a linear system. Kaya mong i-approximate using a linearization technique. Okay? So I just hope na walang ganito masyado sa AMAT 350. Kayo rin yata yung student sa 350, ano? So sana walang masyadong overlap para hindi masayang. If there are overlaps, just let me know, ano, para hindi ko na siya i-discuss. Okay. So the first PDF file that I shared with you in the class site is basically module number 7 in my math 175 class last semester. So paki-ignore na lang yung chapter, yung first etong page na to. It's just a description of the class schedule and the objectives for the module. For us, we will stick to the following. We want to find an LU decomposition for a given matrix. And then probably in the next few meetings, we're going to look at QR decomposition and Cholesky factorization. Okay. And of course, at the end of the section, we will try to use these factorization methods to solve scientific problems. Okay. Now, here we go. Let's talk about matrix factorizations, basically the LU factorization of a matrix. Now, as I've mentioned earlier, matrix inversion is a very costly process computationally and ano pa nga ba? Computationally in terms of complexity at saka sa number At saka sa memory, paggamit ng memory. Kasi marami kang gagamiting memory to store some of the data that you are using in matrix inversion. Okay, and it is highly prone to round off and propagated errors. That's why hindi advisable na gumamit ng matrix inverse sa pagko-compute or pag-solve ng AX equals B. All right. So one of the ideal solutions that would be very helpful in solving linear systems is basically using good old what do you call this? The reduction of A into reduced row echelon form, or actually hindi kailangang reduced row echelon form, pero at least i-reduce natin siya into row echelon form, which is basically we want the matrix A to be transformed into, say, an upper or a lower triangular matrix. Ano nga bang ginagamit natin? Ginagamit yata natin ay upper triangular, no? Doon tayo sanay sa row echelon form. So gusto nating i-reduce si A into, say, an upper triangular matrix via the use of elementary row operations along, actually hindi lang si A, pero yung augmented matrix A and B. Then we will just do back substitution after we got that form. So basically, ang gusto kong mangyari, si A ay gamitan ko ng elementary row operations, which basically ay nandun sa definition mamaya, pero spoiler alert, sila yung interchanging of rows, multiplying one row by a scalar, and the third one is adding a scalar multiple of one row to another row. And your goal is to translate A into an upper triangular matrix. When we say an upper triangular matrix, zeros lahat ng entries na nasa ilalim ng main diagonal. All right? So basically, it looks like U11, U12, U13 until U1n. Tapos U22, U23 until U2n. U33 all the way up to here hanggang UNN. Okay? Tapos equal na kay 0 yung nasa ilalim ng main diagonal. So this is what we call a right upper triangular matrix, or for brevity, upper triangular matrix na lang. Okay. So siyang upper triangular matrix kasi yung upper triangle lang yung merong lamang non-zero entries, or posibleng magkaroon ng non-zero entries, right? And then gusto ko rin palang isama rito to perform the same elementary row operations dun sa augmented matrix AB para ma-solve ko yung linear system. So basically what I do is consider the augmented matrix AB, apply elementary row operations to it. Okay? So magiging ganito yung itsura niya. Okay. Pero naka-augment yung resulting entries mula kay B. Tawagin kong B'1, B'2 until Bn prime. Yung mga resulta when I do the same elementary row operations doon sa right-hand side vector B. All right? So essentially, idudugsong mo si B doon sa matrix A, perform the same EROs you use in the transformation of A into a right upper triangular matrix. Ito yung makukuha nating matrix in row echelon form. Okay? And then, after we have transformed the matrix A into an upper triangular, and we have made appropriate transformations on the right-hand side elements, okay? Pwede na natin itong isolve yung system via back substitution, okay? We say back substitution because here, if you translate it back into equation form, dun sa dulo, meron lang tayong UNN equals Bn prime. And Bn prime is a constant, so we get the value of, or we get the solution, all right? Tapos, gagawin mo lang to rito, you get the values of the variables that you wanted, right? So makukuha mo na U33, sorry, not U33, you get U n-1 column, tapos nasa n-1 times sorry, kulang pala ako. So, kailangan ko siyang ibalik. So, ito ay magiging x equals bn prime. Tapos, ito ay meron kang unknown. So, essentially, you will just do the back substitution. Probably, I'll show you the the exact formulation later, pero yun yung idea. Bakit tayo nag-reduce row echelon form? Kasi ang gagawin mo, magba-back substitution ka na lamang. You did all the transformation here, so essentially here, we get UNN equals BN prime and so on. Hanggang makarating tayo dun sa taas, makuha natin yung value ng lahat ng mga variables. Okay? Now, this is the ideal process because number one, hindi siya kasing, though expensive pa rin siya because this is big O of n cubed, where n is the number of rows or columns of your matrix. So, malaki pa rin yung computational expense in terms of the number of operations required to carry the Gaussian, actually yung pala yung mas tamang term. Aside from reduction to row echelon form, ito yung Gaussian elimination. So sa Gaussian elimination, big O of n cubed, yung number of operations required, tapos hindi siya ganun ka-unstable as matrix inversion. Okay? So that sounds to be a perfect plan to combat the computational expense and the instability caused by matrix inversion. Pero merong mga problema pa rin to kasi hindi siya ganun ka-efficient. Because imagine kung kailangan mong isolve yung isang system AX equals various right-hand sides. So, B sub I ito. Kailangan mo siyang isolve ng maraming beses na iba-iba yung right-hand side vector. Gawin ko pala siyang superscript. Kasi yung subscript siya yung gagamitin nating address or gagamitin nating notations for the components of the vector, right? Pero ang idea rito ay what if you will solve the same system, AX equals B, pero iba-iba yung right-hand side. You can think of it as sa data science, pwedeng ito yung nangyayari kapag nagtitrain ka ng data. Meron kang i-extract na parameters, pero iba-iba yung set of data sets na pinagkukunan mo ng parameters and you want to compare pare-parehas ba yung parameters na na-extract ko with different set of right-hand side data? Alright? So, yun yung problema na, okay, so kung meron akong halimbawa 1,000 na data set, data vectors B. So meron akong B upper 1 hanggang B upper 1,000. Do I need to do Gaussian elimination 1,000 times para lang ma-compare yung mga makukuha kong solution vectors para sa bawat isa dun sa 1,000 matrix systems na yun? Even though I do have the same I do have the same coefficient matrix. So parang sayang yung effort pag paulit-ulit mong gagawin yung Gaussian elimination and the back substitution that comes with it, right? But you can be clever about it. Sabihin mo, hindi naman kailangan kasi pwedeng gumamit ako ng isang mas malaking augmented matrix. So instead na isa-isa kong i-augment yung mga B upper I's dun sa matrix A tapos mag-i-ERO ako para makakuha ng upper triangular matrix at B prime I, alright? Tapos magba-back substitution ako dyan, mas efficient na paraan ay ganito. I-augment ko na lahat ng mga vectors dun sa matrix na to. P3 and so on. Mas malaki na yung matrix na gagamitan ko ng ERO, pero in this particular case, kasi yung elementary row operations naman, lagi lang nakadepende dun sa components ni A o dun sa entries ni A. So whatever I do here, pwede ko siyang gawin sabay-sabay doon sa mga right-hand side vectors B. Alright? And probably that will solve the problem na, okay, ito yung efficient way ng pagsosolve ng sandamukal na AX equals B, na iba-iba lang naman yung right-hand side. Pero there's one problem there. Paano kapag yung B upper I's ay hindi kagad available sa atin all at once? Maybe B sub 1 is available to us, but B upper 2 is something that we only get after doing something on the parameters that we have obtained from B upper 1. Okay? So ibig sabihin parang iterative process siya. Kailangan ko munang i-compute si B1, do some manipulation to the solution from the system involving B upper 1, tapos saka ko pala makukuha si B upper 2. Tapos si B upper 2 siya naman yung ilalagay ko doon sa system. So meron akong AX equals B upper 2. Tapos si B upper 2, kailangan kong i-manipulate pa para makuha si B upper 3 and the solution that I've got from B upper 2. So essentially, hindi ko siya ma-form in this way. So yun yung isang problema. So kailangan natin ng maghanap ng isang efficient way. Paano masusolusyonan yung mga gantong problema? And what I suggest we do is via factorization. Okay? Kasi dito, paglalaruan lang natin yung coefficient matrix A, and then we will have, or we can develop a generic formula para ma-solve yung isang system depending only on the decomposition of A and the right-hand side vectors B. So hindi natin kailangan paulit-ulitin yung big O of n cubed na operations na kailangan natin gawin for Gaussian elimination. Okay, and the first and probably the easiest ay yung tinatawag na LU factorization. Okay, so it's called LU factorization. Hindi masyadong creative yung pagpapangalan, but this is a nice way to remember this decomposition. The LU decomposition or factorization of a matrix A is the writing of the matrix A as a product of two matrices, L and U, where L is lower triangular and U is upper triangular. So lower triangular siya, so ibig sabihin, meron kang diagonal entries, 0 sa taas ng main diagonal, nasa lower triangular, nasa lower triangle lang ng matrix yung non-zero entries, and then upper triangular, siya naman ay 0 dun sa ilalim. So if we are given a matrix A, we want to see if we can split this into two factors. The first factor being lower triangular, that's the L, and upper triangular. That's what the U stands for in the LU decomposition. Okay, so yun yung idea. Paano tayo makakabuo ng LU factorization? And probably what I do in undergraduate classes is basically to tap on what they already know. Okay, siguro ganun na rin yung gawin natin para makita natin yung development. Okay, I have here in definition 7.1, definition ng elementary matrices. Because I want to translate everything in terms of things that we can use in calculations. Okay sana yung sinabi natin na elementary row operations. Kailangan ko lang pagpalitin yung mga rows. Kailangan ko lang i-multiply yung isang row by a scalar. Tapos, pwede rin ako mag-add sa isang row ng scalar multiple ng isa pang row. Those make sense if we are just doing the calculations ourselves. But how can we ask a machine on how to do these operations? Hindi mo naman pwedeng sabihin kay, hindi mo madaling masasabi sa isang computer na ganito yung gawin. Kasi yung elementary row operations ay mas designed for human implementation. So kailangan ko humanap ng mas formal way in the sense of computations. Paano masusulat yung elementary row operations? And apparently, elementary row operations are basically coupled with some elementary matrices. And that's what we have in definition 7.1. So here we define what elementary matrices are. So a matrix E, which is square, so ang size niya ay n by n, it is called an elementary matrix if and only if it is the result of applying an elementary row operation on the identity matrix. Okay? So essentially, may tatlong klase tayo ng elementary matrices. Una, yung elementary matrix na nakukuha mo from the identity by interchanging rows. So ito yung notation ko for interchanging rows. I will change the position or swap the position of row I and row J. And if I do that on the identity matrix, the resulting matrix E is what I call a permutation matrix. Permutation matrix siya kasi binabago niya lamang yung position ng dalawang rows sa isang matrix. Okay? Or ideally, that's the idea. Okay. Second, I can multiply row, there's a typo here. Okay. So dapat ito ay, nagmula ako kay identity matrix, tapos ang gagawin ko, yung ith row ni matrix I, ni identity matrix I, ay papalitan ko lamang ng constant multiple ni R sabay. Another typo, this should be small c. Alright? So ito lamang yung parang gusto kong pang-mimic dun sa elementary row operation na pag-multiply ng scalar sa isang row. So essentially, I perform that scalar multiplication of a row to the elementary matrix. And what I get after doing that is an example of another elementary matrix. Tapos for the purposes of this class, tatawagin ko na lang si E ay isang row scaling matrix. I don't know if there's a formal name, pero para lang sa atin, madaling i-refer na ito yung identity matrix na nakuha, ito yung elementary matrix that we obtained by multiplying one row by a non-zero scalar. Tawagin natin siyang scaling matrix, or in particular, a row scaling matrix. And the third type is, you can guess, this is basically the matrix E that we obtain from adding a multiple of a row to another row, right? Ito naman yung analog ng pangatlong elementary row operation, pero yun nga, i-apply natin siya sa identity matrix. So if you apply if you replace the ith row of the identity matrix by the ith row plus a scalar multiple of the jth row, then we get an elementary matrix. And to have a better reference or an easy reference to such elementary matrices, tawagin natin silang row translating matrix or row translator. Okay. Itong dalawang terms na yan, scaling matrix saka row translator, ay invento ko lang. So wag niyang gamitin sa labas ng klase na to because I don't know if there are formal names for it. Pero if you know the formal names, just let me know. Pero ito yung ginamit kong pseudonym para sa mga elementary matrices nito. So in summary, instead of talking about elementary row operations, because we are looking forward to implementing these algorithms in machines, gagamitin ko ay elementary matrices instead of elementary row operations. And basically what the following example will show us is that eto pa lang, elementary row operations ay hindi lang basta-basta natin ginagawa lexicographically. Hindi lang natin siya ginagawa on face value ng matrix, pero resulta pala siya ng matrix multiplication. So if you want to do an elementary row operation, you simply multiply your target matrix, or pre-multiply actually, or do left multiplication of an elementary matrix to your target matrix, right? So halimbawa, meron akong matrix A, and I want to interchange the row, the third and the first rows. Ang dali niyang gawin, no? Sa elementary row operation, sa alam mo, lexicographically ko lang naman gagawin, yung pagpapalit ng first at saka third row. Okay? So ito yung makukuha ko. So the first row will go to the third row, and the third row will go to the first row, and all other rows remain unchanged. Okay? So ito yung parang lexicographic lang natin na ginagawa. However, if you want this to be done in a computer, we need to have a systematic way. Paano sasabihin kay computer na pagpalitin mo yan, right? And I guess the best way to do it is by doing formal matrix multiplication. And actually, the permutation matrix obtained by doing the exact action that we want to happen to the matrix A, dun muna sa identity matrix. So what I do, again, the target is to swap the first and the third rows of the matrix A. What I do, I get the elementary matrix corresponding to that action. So kailangan yung action na yon gawin ko muna sa identity matrix. And I'll get the matrix E. And this is a permutation matrix because again, this is the I4, the identity matrix with 4 rows and 4 columns, wherein the first and the third rows were interchanged. And then you can check this matrix left multiplied to the matrix A will give us the desired result of the elementary row operation. Okay, so ito yung mas formal na pagpapagawa ng interchange ng rows. Gawin mo muna yung gusto mong row interchange sa identity matrix to get the elementary matrix, and do that and then use that as a left factor to your target matrix. And you see that your product, EA, will be the desired output of the elementary row operation. Okay. Now, I have a bunch of examples here, but you're graduate students, so I know you can do this. Pagpasensya niya kung medyo corny yung examples. This is designed for undergraduate students. This is the first time that they will see these examples, so kaya kailangan marami yung examples na ibibigay. For instance, this matrix F is an elementary matrix because it was obtained by multiplying the second row of the identity matrix by -1. So ito yung notation natin doon. And then if I pre-multiply this to any matrix, the effect of this will be multiplication by -1 of the second row of the target matrix. Okay? Alright, so example 7.3 naman, papakita niya yung row translator. So note that E sub 1 is a matrix that I obtained. Tama ba? Elementary matrix nga ba to? Yes, it is the elementary matrix that I obtained by adding negative 33/4 times the first row to the second row, right? So ito yan, yung row 2, okay, ng matrix E1 ay nanggaling sa identity matrix na 4x4, wherein the second row is replaced by the second row, parang may mali, dapat ito ay plus R2 plus negative 33/4 R1. And that's how we get E1, right? So if you want to do this row translation in terms of a row of formal operations, ang gagawin mo, E1 times the target matrix. Because whatever happened to the identity matrix after you do one ERO, yun din yung makukuha mong output pag in-apply mo yung matrix na yon sa yung elementary matrix na yan sa kahit anong target matrix. Okay? So essentially, you see what I'm trying to build up here. Kasi kung matatandaan nyo, yung pag-reduce or pagsusulat ng isang matrix in reduced row echelon form, or when you do the Gaussian elimination, ang ginagawa lang naman natin, nagbo-multiply tayo kahit sa equations, even if you're not familiar with how to manipulate these matrices. Pag meron kang linear system, mag-elimination ka, ang ginagawa natin, nagbo-multiply tayo ng isang scalar sa isang equation, tapos i-add natin yon dun sa pangalawang equation para mag-zero yung isang variable o yung coefficient ng isang variable, effectively reducing it. Alright? Kung sanay kayo ng linear algebra, ito yung nire-reduce natin siya para magkaroon tayo ng upper triangular matrix. So the idea here is, ita-translate ko lang yung ginagawa kong elementary row operations kapag ako ay nag-Gaussian elimination o pag ako ay nagre-reduce ng isang matrix to row echelon form, okay, into a bunch of elementary matrices. Okay, so for instance, okay, we have the matrix A again. Tapos gusto ko siyang masulat in an upper triangular form. So I start here and I want to end up with this. So traditionally, ang gagawin niyo dito sa Math 120 or sa inyong linear algebra class, you will perform elementary row operations. Pero ngayon, ifo-formalize natin siya. So I'll just take note of what are the elementary matrices involved in this particular process. All right? Wala tayong problema sa first row kasi pwede ko yung i-maintain. Ano? So pwede siyang, pwede kasing siya na rin yung top row dun sa upper triangular matrix. Okay. Now the problem is we want everything below the leading entry of the first row to be equal to 0. So kailangan mag-isip ako paano ko ito magagawang 0, magagawang 0, magagawang 0 by just performing elementary row operations. Okay. So first thing, I can replace the second row by the second row minus, kailangan mawala ito. So kailangan mag-multiply ako ng what? Mag-multiply ako ng negative 3/4 dun sa first row, okay? Para maging negative 3, i-add ko siya dun sa second row, magzi-0 siya. But we do this for all entries. So basically what I want to do is to replace R2 by R2 minus 3/4 of R1. And I will get this row. And I will do this for the remaining the remaining rows. So yung R3, papalitan ko ng R3 minus 1/2 R1. Tapos si R4, papalitan ko ng R4 minus 1/4 R1. Ito yung makukuha natin. Ito yung ginagawa nyo sa linear algebra. Na, okay, lexicographic lahat ng pangyayari. Sinasabi ko lang, ano yung row operation or row operations na ginagamit ko to arrive from one matrix to another. Pero ngayon, gusto natin siyang i-translate into matrix multiplication para mas formal yung dating niya. And this is something that we can implement in a machine. All right? Then, kung nandito na tayo, hindi pa siya naka-row echelon form kasi sa ilalim ng leading entry ng second row, meron pang mga non-zero elements. Gusto ko nga maging upper triangular siya. So I will do the elimination process again. I'll perform the following row translations para makuha ito. And then lastly, kailangan ko itong 10/7 ay mawala. So I'll do another row translation and finally get this upper triangular matrix. Okay? So na-refresh na ba? Naalala na yung pag-reduce, hindi pala reduce row. Lagi akong reduce row, pero row echelon form lang naman to, no? Kasi hindi natin kailangan 1 yung leading coefficients. Alright? At hindi ko rin kailangan mag-0 yung mga entries, yung mga ibang entries. Hindi ko siya gustong maging diagonal. So gusto ko lang siya ay maging upper triangular. Okay? So if you want to see the formal way of doing it, when I say formal, ito yung mas madaling ipagawa sa computers. Kailangan, itong mga elementary row operations na to ay i-perform mo dun sa identity matrix para makuha yung pang left multiply. Alright? So halimbawa, itong, silipin ko yung sinulat ko. Yeah. Itong R2, itong first translation na to, yung replacement by R2 by R2 minus 3/4 of R1, yan muna yung una kong i-model. At ito yung E1 na nakita natin kanina. Dapat pala ito ay 3. Sorry, may typo ulit. So dapat siya ay 3. So para makuha ko yung elementary matrix kanina. And I'll call that E1 because basically just to keep track pang ilang elementary row operation ko siya ginawa. Kasi magmamatter to kasi di ba left multiplication yung gusto kong mangyari. And then here, gagawin ko ulit to sa identity matrix to get my second elementary matrix. Right? So if I do that, I'll get this and this would be my E2. Basically the third row of the identity matrix replaced by its third row minus 1/2 of the first row. I'll get E2. And then same level, ito yung pangatlong elementary row operation, makukuha ko naman ito. So basically, kung anong ERO yung ginamit nyo or ginawa nyo dun sa target matrix, gawin nyo lang siya sa identity matrix para makuha yung elementary row operation para dito. Okay? Now, you need to keep track of the order, pero luckily, dito sa first run ng elimination process, we can do the 3 operations in any order. Pwedeng mauna ito, or pwedeng mauna ito. So it doesn't matter in which order you will perform these 3 EROs. Same output lang yung makukuha natin. Kaya I'm not very particular with the ordering of these 3 operations. Okay? So pwede nyo itong pinag-jumble-jumble, iba-iba yung ginamit nyo na E1, E2, and E3. Okay? Pero hindi nyo pwedeng gawing E1 yung nandito sa second level. Alright? So i-reserve nyo to, dapat na-perform mo na yung unang 3 EROs before you do these 2 EROs. Okay? So ibig sabihin, dapat na pre-multiply mo na yung target matrix by the elementary matrices corresponding to these EROs before you pre-multiply the result by one of this or by one of the elementary matrices that will come from etong dalawang EROs na ito. Okay? Tapos, ganun din sa dulos. Dapat guaranteed, ito dapat yung nasa pinakakaliwa kasi ito yung huli kong i-apply. Right? So you can check that that E6 times E5 times E4 times E3 times E2 times E1 times A will give us the upper triangular matrix. So ito yung translation ng lexicographic operation na ginagawa natin sa 120 or sa AMAT 105 into a more formal matrix operation implementation. All right. Now again, you can also check that this would be equal to what? E6, E5, E4, E2, E1, E3 times A. You'll get the same matrix, even though in general, matrix multiplication is not commutative, right? Pero alam natin, itong unang 3 matrices na to, ito yung unang salvo ng Gaussian elimination pass na ginagawa natin, and any of them can go first, right? So hindi nagba-matter kung sino yung unahin ko sa kanila. But again, E5 cannot go first before E3 or E2 or E1. All right, so by level yung pag-arrange. Okay? And then dahil magta-time na, sorry, naubos yung oras natin pagko-connect at reconnect. Pero the idea here is that this guy actually would be lower triangular. Ito ay magiging lower triangular matrix, let me call this L prime, okay? At ang tanong, paano natin magagawa yung LU decomposition? Siguro, spoiler, bawat isang ito ay elementary matrix, the product would be lower triangular. Okay? So itong product na to ay magiging lower triangular, tapos lower triangular siya, tapos ang inverse ng lower triangular ay lower triangular din. So i-invert ko lang ito. Ito yung L sa ating LU, or yung inverse nito, siya yung L dun sa ating LU factorization. Tapos yung A, siya naman yung ating, CU, siya yung upper triangular dun sa decomposition. Okay? So if you have some time, you can take a look at the exercises. So usually I ask my students to perform the product E6 to E1, and then they will see that, oo nga no, ito ay isang lower triangular matrix. Actually, it's not just a lower triangular matrix, it will be a unit lower triangular matrix. Ano yung unit lower triangular matrix? One yung nasa lower diagonal. One yung nasa main diagonal niya. And then I will introduce some bunch of theorems to them. Okay, ng elementary matrices ay laging invertible. Tapos alam natin na kapag ang product ng mga tama ba? Ang product ng invertible matrices ay invertible din. Napaisip ako bigla. Totoo ba 'yun? Kapag ka si AB so yung product ay kapag ka si A at saka si B ay parehong invertible. So yung B inverse times A inverse, siya yung inverse ng product. Ano? Tama nga ba? Tama to. Totoo to. Pero I was thinking, kapag ka ba invertible yung product, totoo ba na invertible yung factors? Yeah, let's ponder on that. Pero ito yung mga importanteng theorems para ma-establish ko kung yung factorization. Ano? So elementary matrices are invertible. We can write a proof for it. Theorem 7.2, the product of two unit lower triangular matrices is also unit lower triangular. And this is usually after we have established that this product is a lower unit triangular or a unit lower triangular elementary matrix. Ang haba ng kanyang pangalan. And then para magamit ko tong huli, the inverse of a unit lower triangular elementary matrix is also a unit lower triangular elementary matrix. Okay? Tapos tingnan natin yung proof next time, all the way up to finding an LU factorization for the matrix A. Again, this is a special LU factorization because L will be a unit lower triangular matrix. A lower triangular matrix with ones in its diagonal. Ang tawag dito ay Doolittle factorization. So basically, the Doolittle factorization is obtained by just performing Gaussian elimination, taking note of what the elementary row operations you use to get to the upper triangular matrix, converting those elementary row operations to elementary matrices, and then taking their product, then inverting the product, or simply multiplying their inverses, and then you're gonna get the matrix L. Okay? Pero makikita natin next time, meron pang ibang lower triangular, mayroon pang ibang LU factorization. Ano? And we'll see that on Wednesday na. Alright? Okay, so I think I can stop here. Yeah, apologies for the disconnection kanina. But kaya medyo okay lang din na mag-overtime tayo ng konti. Any questions? So what do you think? Masyado bang basic yung pinag-aaralan natin or okay lang naman? Baka sabihin nyo, corny na nito. Alam ko na to, sir. So bakit pa natin pinag-aaralan? Ano? So if you're already familiar with it, just let me know para hindi na natin siya dadaanan next time. But if you want to go through the journey, Doolittle factorization, then we'll do Kraut factorization, and then QR decomposition next week. Then we can carry on with the module. All right? Any questions? Clarifications? Wala naman? Okay, so if there are none, so thank you guys for bearing with me this afternoon. Hopefully next meeting we can cover more things kasi ngayon parang 30 minutes yung interview. Tapos Tapos naputulan pa ako ng internet, ano? So yeah. Oh, Michelle has a question. Go, Michelle.
Sir, more on terminology lang siguro. Siguro, Sir Ben, sir can also answer. Kapag po ba, sir, in-automate yung any factorization, ang tawag po ba dun is machine learning? For example, in-automate natin through MATLAB or Python, is that what we call machine learning?
Yung actual LU factorization.
Yes, sir. If we automate, for example, kahit anong matrix ang i-enter natin doon sa program,
Uh-huh.
uh, uh, i- machine learning na po ba yung tawag doon?
I don't think so. Hindi pa siya yung machine learning, ano? Kasi parang wala pa tayong fini-feed na data sa kanya and we are doing everything for the machine. Kasi pagka nag-write ka ng program para sa, say, sa LU factorization, ano, i-automate mo siya, pero all of the calculations ay gagawin na natin. So essentially, there's nothing more for the machine to learn or for the machine to think for itself kasi i-lay down na natin yung instruction. Kasi mamaya ibibigay ko na or next meeting, ibibigay ko na kung ano yung formula para makuha yung elements nung lower triangular matrix L at nung upper triangular matrix U. Kasi ayaw naman natin na every now and then ay kukunin ko pa yung LU. Kasi baka yun yung nasa isip mo, no? So, pag meron akong matrix A, kailangan ko siyang elementary row operation. Tapos, i-convert ko yung elementary row operation sa elementary matrices, i-multiply ko and so on. Pero the idea here is, kaya ko siyang gawin deterministically. So, kasi kaya kong i-determine via simple generalization, ano yung itsura ni L, ano yung itsura ni U, depende dun sa itsura ni A. Right? So we can algebraically determine the components of A and U depende dun sa itsura ni A. I guess what we call machine learning is something that hindi natin kayang gawin deterministically. So if you have, say, a bunch of data, you want to learn the different characteristics of that data. So ang gagawin mo, meron kang isang black box, so meron kang isang system, which basically could be a linear system in nature, or it could be a regression method, or it could be some other tools, ano, nang gagawin niya ay maghahanap siya ng relationship between those data to get the parameters. So basically, the machine will build up the model for us. Right? Pero dito kasi sa gagawin natin sa LU factorization, tayo yung maghahanap ng formula by hand doon sa ano dapat yung laman ni L, ano yung laman ni U. So basically, this is just one tool na pwede natin gamitin pag nag-machine learning na tayo. Kasi pwede mong tingnan isang machine learning algorithm ay gumagamit ng linear systems pag solve ng unknown parameters. So dahil yun yung gagawin mo, lagi siya nata-translate sa AX equals B, where B is a bunch of data that you got from your database. Ano? So ang machine learning doon ay paano natin mas matuturuan si computer o si black box na nakunin yung characteristics ng data, pero in order to do so, kailangan marunong siya mag-LU factorization. Kasi magsosolve siya ng isang linear system ng paulit-ulit. A linear system with different right-hand sides. So, tool pa lang tong LU factorization sa posibleng maging machine learning algorithm. Okay? Kasi nga, kaya pa natin tong i-compute algebraically. So ang problema, pag meron kang 1,000 data, gusto mong kunin, say, yung similarity nila o ano yung parameters na nagde-describe doon sa data na yon, or gusto mong gumawa ng model, alam mo na yung general itsura ng model but you don't know what the parameters that come with the model, you can train the model, or you can ask a machine learning algorithm to learn for you what the parameters of the model are. And inside that black box, which will output the parameters for your model, yun yung papagawa natin yun yung gagamitan natin ng LU factorization. So yung LU factorization, nasa loob siya ng black box na ginagamit mo for machine learning. So I hope I got your question and I hope I answered it kahit maiksi lang.
Yes, sir. Thank you po.
All right, so other questions? Okay, so if there are none, then we'll continue on with this. We'll continue on Wednesday with this module, and hopefully we can start with the next module, which is about QR factorization. And until then, guys, keep safe, enjoy the weekends, and see you on Wednesday. Bye.
Thank you, sir. Bye-bye.
Thank
All
you
right.
po. Thank you po.
Thank you po. Happy weekend.